Hi, I'm Daniele Sorini, a postdoc at the University of Edinburgh, and I'd like to present my recent work where I consider the results of different runs of the Simba cosmological simulations and compare them to observations of a Lyman-alpha absorption around quasars at redshift 2.4. The goal was first to verify to what extent the simulation reproduces the data, and second, to assess the impact of different feedback prescriptions on the properties of the CGM of quasars. Here I'm listing the main physical features of the Simba simulation, obviously referring you to the original paper by Dave and others for the details. I would just like to briefly emphasize that Simba distinguishes between a torque-limited model for accretion of cold gas onto the black hole and boundary accretion for hot gas. The AGN feedback prescription follows three different modes, which are AGN winds, jets, and X-ray heating, depending on the accretion rate of the black hole and on the gas fraction of the host galaxy. Our fiducial run is a 100 megaparsec over H box, and then we also have several 50 megaparsec over H variants that include only some of the feedback modes. We select quasars in Simba as the black holes with the fastest accretion rate. If you're interested in exactly how we determine the accretion rate threshold in our selection criterion, please check my paper. Once we select the quasars, we then generate Lyman-alpha absorption spectra along lines of sight in different bins of impact parameter, following exactly the same binning as in the observations. Specifically, we consider the average Lyman-alpha absorption around quasars measured by Prochaska and others as part of the Quasars Probing Quasars observational campaign, and the Lyman-alpha quasar cross-correlation measured by Fonturibert and others from the BOSS survey data. Now, combining these two datasets enables us testing the simulations over 3 decades of transverse distance, hence covering both the CGM and IGM. The green line here shows the results from the Simba fiducial run compared to 2 other simulations, Nyx and Illustris, that I analyzed in a previous work. Within 100 kiloparsec, Simba predicts much more absorption, but all simulations tend to agree as one moves away from the quasar. On large scales, the data are very constraining, but less so closer to the quasar, owing to the smaller quasar pair statistics. However, upcoming observations, such as WEAVE, in which I'm currently involved, promise to obtain many more close quasar pairs, such that the error bars will shrink within 1 megaparsec from quasars, hence giving us more constraining power also on smaller distances. So this is an exciting prospect for the future. We then compared the results of the Simba variants with different feedback prescriptions within the same datasets. The orange line here represents the run with no feedback at all, neither stellar nor AGN. As stellar feedback is activated, we then see a larger absorption within 100 kiloparsec of the quasar. But if we activate the 3 AGN feedback modes on top of that, we barely see any difference. Indeed, also other works related to Simba, as well as another Simba paper that I currently have in preparation, show that the effect of AGN feedback, and particularly jets, becomes evident only after redshift 2, that is, lower redshift compared to the quasar sample considered. This thus suggests that, according to Simba, between redshift 2 and 3, stellar feedback is the main driver of the differences in the absorption profile. We verified that this is the case also for the median radial profiles of hydrogen density, temperature, and radial velocity around Simba quasars. In these plots, the solid lines refer to the median values across the selected halos, and the dotted lines show the 16th, 84th percentiles of the distribution. I thus leave you with the main conclusions of our work. If you have any question or if there is anything that you wish to discuss, please do not hesitate to get in touch. Thank you so much for watching this video.